we can discuss more in the future. So and now it's already 8 a.m. in Beijing time, and your time is 5 p.m. So maybe we start.
Sure.
Yeah. Okay. Could you share your screen, and I will just give a brief introduction for you. Uh,
It says someone else is sharing at the moment. So,
oh yeah. So Jim, could you stop the sharing, and Ben will share. Uh, or maybe I give a brief introduction first, then you can share. Okay. Mm.
I still get someone else is sharing. Host doesn't
Uh, yeah.
multiple.
So I just ask Jean to Jean, could you stop sharing? Maybe I give a brief introduction first, then you can then I think she will, yeah. Okay, so hello everyone. Welcome to the Future Ocean the forum. So I'm Feng Fei Song, uh, a professor at the Ocean University of China Academy of Future Ocean. I'm also the host of today's seminar. It's our great honor to have Professor Ben Santer from Lawrence Livermore National Lab. Before we comment, I just take a moment to provide a brief introduction to Professor Ben. Ben is an atmospheric scientist. He just recently retired from Lawrence Livermore National Lab. He studied natural and human footprints in observed climate record. His early research contributed to the historical 1995 conclusion of intergovernmental panel on climate change. The balance of evidence suggests a detectable human influence on global climate. I think this is very important for our current the global warming study. He served as the lead author of a key chapter of that report. I think that's the first IPCC report. Since 1995, Ben has identified human footprints in atmospheric temperature, water vapor, ocean heat content, sea surface temperature in hurricane formation regions, and many other climate variables. Ben has also received a number of awards for his research that include a MacArthur Fellowship, membership in the U.S. National Academy of Science, and John Carty Award from the NAS. And recently, he also received the MS Roosevelt Medal, the highest honor in our community. So I think this today he will talk about the human influence can be even detected even one century before, even before the car appear. So welcome. Take away, Ben.
Thank you very much. Can everyone see my screen?
Yeah, sure.
So I'm really sorry for last week. It was the first time in my 45 years that I've missed a lecture. My apologies for that. I'm happy to talk to you today about some new work that I've been doing with my colleagues Susan Solomon at MIT, David Thompson at Colorado State University, Chung Fu at the University of Washington, and Yawei Li, also at MIT, in Susan Solomon's group. And this is a piece of research that addresses a simple question. When could we have known that humans were changing global climate? But first of all, a little about myself to complement what Feng Fei just said. I'm a US citizen, but I grew up in the UK and in Germany. My research tries to disentangle human and natural effects on climate. And my big hobby and passion in life is rock climbing, which I do with my son. This was taken just last year at the beautiful high country above Yosemite, a place called Tuolumne Meadows. My son has all the responsibility now. He does the leading. My job is just to follow him up stuff like this. Let me start at the logical beginning point of this work for me, and that was with Suki Manabe, who in 1967 published what's been called one of the most famous papers in climate science, with the title Thermal Equilibrium of the Atmosphere with a Given Distribution of Relative Humidity. Suki and his colleague, Dick Weatherald, at the Geophysical Fluid Dynamic Lab in Princeton, did an experiment with a simple radiative convective model. So this model resolved global mean temperature changes in different layers of the atmosphere. And Suki and Dick, in this simple model, increased atmospheric CO2 from 150 to 300 to 600 parts per million. And when they did that, they found that the stratosphere cooled and the troposphere warmed. CO2, the increase in CO2, more effectively trapped heat in the troposphere. And the logical physical consequence of that was cooling of the stratosphere, with cooling getting larger the higher up you got above the Earth's surface. In a very real sense, this was a prediction, because this is 1967. We don't really have satellite-based measurements of stratospheric temperature. We do have some weather balloon measurements of the temperature of the lower stratosphere, but most weather balloons didn't have the structural integrity to get higher up into the stratosphere. They burst. So we really were not able to probe back in the 1960s this layer of the atmosphere very well and determine whether the prediction made by Suki Manabe and Dick Weatherald was correct or not. The next starting point for me was with this gentleman here, Klaus Hasselmann, who in the 1970s and 1980s was the director of the Max Planck Institute for Meteorology in Hamburg. In 1979, Hasselmann had published a paper in a very obscure conference proceedings in which he outlined a technique for separating a coherent human-caused warming signal from the background noise of natural climate variability. And I should have mentioned that Suki Manabe and Klaus Hasselmann were co-recipients of the 2021 Nobel Prize in Physics, in Manabe's case for improving our understanding of the variability of the climate system and the response to human-caused CO2 increases. And in Hasselmann's case, it was for introducing the world to fingerprinting. What did Hasselmann do? So back then in the 1970s, people were using general circulation models, increasing atmospheric CO2, and they were looking at the changes, say, in surface temperature in response to CO2 increases at individual grid points on the Earth's surface. Hasselmann's real insight was, don't do that. Don't look at individual locations if you're trying to identify a human effect on climate. Look at global scale patterns, because then you may be better able to distinguish between a large global scale human-caused surface temperature signal and the smaller scale noisier patterns of natural climate variability. I went to the Max Planck Institute to do my postdoc with Hasselmann in 1987, and my job as a young postdoc was to implement Hasselmann's fingerprint ideas and to apply them to actual real-world data, which my colleagues and I did in a paper in Nature that was published in 1996. The first thing that we looked at was the vertical structure of atmospheric temperature change, in this case from the North Pole to the South Pole, and in slices through the atmosphere from close to the Earth's surface up to 20 kilometers above the Earth's surface. In simple model simulations that were available back then, we looked at the simulated response to simultaneous changes in CO2, in human-caused particulate pollution, things like sulfate aerosols, and in human-caused stratospheric ozone depletion. We also looked at weather balloon data sets available back then, developed at the Geophysical Fluid Dynamics Lab in Princeton, and were able to show that there was some large-scale similarity between the model predicted vertical fingerprint of temperature change in response to CO2, sulfate aerosol, and ozone changes, and what the weather balloons actually showed over the period that we had weather balloon observations back then. There were some differences between simulations and observations, most notably here over the South Pole, where the weather balloon inferred cooling of the lower stratosphere was larger than in the model simulations. But to first order, both the simulations and observations showed the fingerprint predicted by Manabe and Weatherald back in 1967. Coherent warming of the troposphere across all latitudes and coherent cooling of the lower stratosphere. The problem with this early work was we couldn't get into the mid to upper stratosphere where Manabe and Weatherald had predicted we should see the clearest radiative cooling signal of CO2 increase. So a couple of years ago, together with a number of colleagues, including Chengxi Xu, who has been one of the primary developers of satellite-based estimates of temperature change in the mid to upper stratosphere, Chengxi Xu's work had really resolved some of the differences in satellite-based estimates of mid to upper stratospheric temperature that existed between his satellite-based estimates and estimates obtained by the United Kingdom Meteorological Office by John Nash et al. And Chengxi and his group nicely showed that there were no longer really significant differences in these two groups' estimates when one properly accounted for the effects of satellite orbit drift and instrument calibration issues. That better understanding of the observed changes in temperature enabled us to publish this paper back in 2023, where our bottom line conclusion was that extending fingerprinting beyond the lower stratosphere, beyond 20 to 25 kilometers above the Earth's surface, into the realm of the stratospheric sounding unit temperature measurements was powerful. And it showed that the vertical structure of temperature changes from the surface up to about 50 kilometers provided perhaps the clearest evidence of human effects on climate. So what did we do? Like I said, the initial work comparing and confronting model simulations of the vertical structure of temperature change with observations focused on the lower stratosphere. And it used so-called microwave sounder unit measurements of the microwave emissions from oxygen molecules to probe the temperature changes in different broad layers of the atmosphere, the lower troposphere, the mid-troposphere, and the lower stratosphere. Chengxi Xu's work, however, really gave us these measurements here from the stratospheric sounding unit, again from satellite-based microwave sounders, but now getting up into roughly 50 kilometers, 45 to 50 kilometers. This SSU channel 3, the peak of the weighting function is at about 45 kilometers. That's where it receives the bulk of these microwave emissions. So the bottom line is we were able then in the last 5 or 6 years to push fingerprinting into the SSU, the stratospheric sounding unit domain, into the mid to upper stratosphere. And when you did that, these are measurements from Chengxi Xu for the stratospheric sounding unit and from remote sensing systems in Santa Rosa, California, for the lower stratosphere and the troposphere. When you look at these measurements for the longest continuous period of record, the 39 years from 1986 to 2024, what they show is exactly what Manabe and Weatherall predicted back in 1967. Warming of the stratosphere, cooling of the troposphere. As you can see, the cooling amplifies the higher up you get into the stratosphere here. And in the troposphere, you see this coherent warming, with largest warming over the Arctic, in part because of feedbacks associated with snow and sea ice in the Arctic, and this roughly 50% decrease in Arctic sea ice coverage that we've observed since the late 1970s. So how might we, and how did we, do fingerprinting with the vertical structure of atmospheric temperature change several years ago in this 2023 paper I described? Let me give you a brief cartoon explanation of how fingerprinting works. Imagine that you have satellite measurements of the vertical structure of atmospheric temperature, again, from the surface going up to about 50 kilometers. And what I'm going to show you here are slices through the atmosphere from the South Pole to the North Pole, and again, up to about 50 kilometers. These are the satellite data, and I'm not going to show you every year. I'm going to show you every 3 years, just to give you some sense of how the vertical structure of atmospheric temperature changed in the real world. So we're marching through 3 years at a time. You can see that over time, what's happening here is that the troposphere is beginning to warm and the stratosphere is beginning to cool. And the last year I'm going to show you shows that very clearly, that tropospheric warming coherent across all latitudes and stratospheric cooling in 2024. Now what we can do is we can take the latest, greatest model simulations from phase 6 of the coupled model intercomparison program and look at simulations with human effects on climate from many different climate models and estimate from the models the pattern of vertical temperature change in response to human-caused greenhouse gas forcing. And you can see that there is some similarity between the model predicted human fingerprint and what actually happened, this progressive warming of the troposphere and cooling of the stratosphere in the satellite data. What we can do is use some measure, some simple measure of pattern similarity between the time evolving sequence of observed patterns of change and the model predicted human fingerprint. And this measure of pattern similarity, which is what you can see here, starting in 1986, ending in 2024, shows an increase over time. It shows a trend, which confirms what we can see with our eyes, that the spatial similarity between the satellite data and the fingerprint is increasing over time. But in addition to this trend over 39 years, there's lots of short-term variability, and we understand many of the causes of this short-term variability. This decrease in pattern similarity, for example, in 1992, is caused by the effects of the eruption of Mount Pinatubo in the Philippines. Pinatubo warmed the stratosphere, which is what you can see here in 1992, and cooled the troposphere. Why is that? Pinatubo was powerful enough to inject massive amounts of sulfur dioxide into the lower stratosphere. Some of that sulfur dioxide oxidized and formed liquid phase sulfuric acid droplets. Those droplets absorbed some fraction of incoming solar radiation, outgoing long wave radiation, heating the lower stratosphere and preventing some of the incoming solar radiation from penetrating into the troposphere, thereby cooling the troposphere. So the effects of Pinatubo were the converse of this human-caused fingerprint, which is why you see this dip here in this measure of pattern similarity between the fingerprint and the satellite data. What we're going to do here is look, first of all, at where this measure of pattern similarity over 39 years between the satellite data and the fingerprint falls. And the next thing we're going to do is develop a so-called null distribution, a distribution of pattern similarity between the fingerprint and natural climate variability alone. And I'm going to show you how we do that in the next sequence of cartoons there. And then we're going to compare what natural variability might give us in terms of similarity with the fingerprint with this red line, what we actually got with the satellite data. So let's do the same thing. We have from phase 6 of the coupled model intercomparison project, many thousands of years of control run data. These are so-called pre-industrial control runs with no year-to-year changes in external forcings. So no human-caused changes in greenhouse gases, particulate pollution, stratospheric ozone. What we see is purely the intrinsic variability of the climate system in model world associated with things like El Niños, La Niñas, Pacific decadal oscillation, longer timescale fluctuations like the Atlantic multi-decadal oscillation. And what I'm going to do is march through these control run estimates of the vertical structure of temperature change, 300 years at a time, again from the North Pole to the South Pole, and from the surface right up to 50 kilometers. And in order to make this kind of comparison, what we've done is we've sampled the model simulations with the weighting functions I've shown you earlier. So essentially, we're flying satellites through the model simulation output in order to have an apples to apples comparison with actual satellite measurements. So here we are, we're going through these control runs from many different climate models, 300 years at a time. And what you can immediately see is that the variability in the control runs is much smaller scale than in the fingerprint, the human influence fingerprint, or in the satellite data. Natural climate variability is small scale and noisy. It doesn't give you simultaneous, coherent warming of the entire troposphere and cooling of the entire stratosphere. So in the same way that we did for the satellite data, we can take these control run patterns of variability of temperature in a world without human influence. We can compare them with the human influence fingerprint. And again, we can generate the same measure of pattern similarity. And I'm using the same y-axis range here that I used for the comparison with the satellite data earlier. I'm just showing the first 400 years of this pattern similarity metric. Again, it shows you what you can see by eye here, that on 39-year timescales, which is what you can see here in terms of the trends that I fit to this pattern similarity time series, there isn't much similarity over 39 years between the search for human influence fingerprint and natural climate variability in model control runs. Again, we have thousands of years of control run data, so we can build up a distribution of these trends of natural similarity between the fingerprint and control run variability. And that's what you see here in blue. That's what this PDF is. And it has some desirable properties. So it's centered on 0, which is nice. It tells you that on average, in control runs, you don't have large similarity between the search for human influence fingerprint and variability on timescales of 39 years. Some 39-year periods, by chance, look a little bit like the fingerprint. Some on this side don't look like the fingerprint, look like the converse of the fingerprint. But the key point here is that this is what we got when we compared the fingerprint with actual satellite data. So it's virtually impossible, if under the proviso that the CMIP-6 simulations of internal climate variability are realistic, which an assumption we'll return to later, it's virtually impossible to get this degree of pattern similarity that we actually got by natural climate variability alone. Why? Why is that? Again, it's because there's a fundamental mismatch between the scale, the spatial scale of human influence on the vertical structure of temperature, this globally coherent warming of the troposphere, cooling of the stratosphere, predicted by Manabe and Weatherall back in 1967, natural climate variability in coupled model control runs looks nothing like that. It's much smaller scale. You see these anti-correlations between the tropics and the extratropics, or you see anti-correlated structures between high latitudes in the northern hemisphere and in the southern hemisphere. So folks like Chung Fu and Susan Solomon and others who study the Brewer-Dobson circulation in the stratosphere, this sort of pattern of variability that you see here in the control runs makes sense to them. It's in accord with our physical understanding of the smaller scale structures of intrinsic variability in the real world. And again, it's this fundamental pattern mismatch between the human fingerprint and the smaller scale structures of natural variability that gives us the result I just showed you here. The satellite data look like this. They don't look like this. Just to reinforce this message, this model predicted vertical fingerprint is robust across a range of different models. We looked in our 2023 PNAS paper at 9 different CMIP-6 models. These were models that had sufficiently high tops and sufficient vertical resolution in the mid to upper stratosphere to enable us to calculate synthetic SSU, stratospheric sounding unit temperatures, from the model simulation output. All 9 of these models show this same large-scale pattern of warming of the troposphere, cooling of the stratosphere, and stratospheric cooling amplifying the higher up you get. So this is in accord with what Manabe and Weatherall predicted, a robust pattern across models. The physical drivers of this pattern are well understood, and we see qualitatively very, very similar tropospheric warming, stratospheric cooling in the latest, greatest satellite measurements for the period that we have continuous measurements from 86 through to 2024. Well, Fengfei mentioned that I'm retired. I'm failing retirement pretty miserably, I think it's fair to say. And in the last year, together with my colleagues at MIT and at Colorado State University and the University of Washington, Chung Fu, I've considered this question, and it's a simple thought experiment. Imagine that back in 1860, we had the satellites that we have today. And we had the capability back then to accurately measure global changes in temperature up to about 50 kilometers as accurately as we can today. When in this hypothetical world could we have first identified with high confidence a human fingerprint on global climate? So here are some of the assumptions underlying this thought experiment. Assumption 1 is, again, that the capability back in 1860 to monitor temperature was there, and that we could do it globally. and that the instruments that were available in this hypothetical world had the same accuracy as today's satellites. Another assumption is that the monitoring period was 40 years long, so roughly the same length as we have now in the actual satellite data. Another assumption is that in the model simulations that we're going to be looking at, they have reliable estimates of the actual changes in CO2 that happened from 1860 through to the present. So, of course, in 1860, we didn't really have direct observational measurements of atmospheric CO2, but we've used things like ice cores in Antarctica and Greenland to make inferences about the levels of CO2 that we think existed back in 1860 and how those levels changed as a function of time. So in order to do this thought experiment, we're going to use historical climate change simulations from phase 6 of the coupled model intercomparison project. We have results from 9 different state-of-the-art Earth system models. Again, these are models that have sufficiently high tops and sufficient resolution, vertical resolution, in the mid to upper stratosphere to enable us to calculate synthetic satellite temperatures from the model simulation output. This yields a total of 32 individual realizations of historical climate change from 1850 to 2014. And because we want to compare beyond 2014 with actual satellite data, we spliced together the CMIP historical runs, which end in December 2014, with results from these SSP simulations, these shared socioeconomic pathway simulations. And in this case, we're going to use SSP5 from 2015 to 2100. As I mentioned, the estimates of intrinsic climate variability are obtained from, in our case, over 4,000 years of pre-industrial control runs performed with the same 9 high vertical resolution, high top models. We also analyze satellite temperature data from 3 different research groups in the lower stratosphere and in the troposphere. Those are from Chengxi Shu's group at the University of Maryland, from the University of Alabama, and from Remote Sensing Systems in Santa Rosa. More components of the thought experiment. We're going to look at a global domain, 90 degrees north to 90 degrees south, zonal mean changes in that global domain. We also look only in the southern hemisphere, only in the northern hemisphere, and we also look only at mid-latitudes in the northern hemisphere, between 40 north and 55 north. That's where some of the first weather balloon measurements were made in the early 1900s by Tesserenc de Bort and a German scientist, Richard Assmann. We're also going to look at 4 different groupings of atmospheric layers. Let me show you what those groupings look like. So here are, for the period of satellite record, the changes in the temperature of the lower troposphere from the surface to about 8 kilometers, the temperature of the total troposphere from the surface to about 13 kilometers, the temperature of the lower stratosphere, roughly 15 to 20 kilometers. And these are these 3 SSU channels, 25 to 30 kilometers, 35 to 40 kilometers, and about 40 to 45 kilometers above the surface. The black line there is the multi-model average from these 9 CMIP6 models. The gray envelopes are the 32 individual realizations of historical climate change spliced together with SSP5 after 2014. This purple line, this is Chengxi Shu's SSU data. Changshishu is the only one who provides global scale stratospheric sounding unit measurements that we could use in this study. And in the troposphere, the red, and in the lower stratosphere, this red line here is the average of these three groups: remote sensing systems, the University of Alabama, and Changshishu's group here. These green lines are the dates of big volcanic eruptions. So here's Pinatubo. As I mentioned, again, Pinatubo causes this warming of the lower stratosphere. And the warming is largest in the lower stratosphere, where most of the volcanic aerosol resides. It decays the higher up you get into the stratosphere. These smaller lines are so-called small volcanic eruptions. This is Tavurvur in Indonesia. This is Nabro in Eritrea. And Susan Solomon and I have, together with Cheng Shishu and Cheng Fu and another number of others, looked at the signals of these quote-unquote small volcanoes in tropospheric temperature and showed that even though they weren't Pinatubo class eruptions, they still cooled the troposphere, as you can see here for both Nabro and for Tavurvur here. The kicker is that we're going to look in this fingerprint study at three different groupings of layers: the mid to upper stratosphere, the so-called SSU grouping, stratospheric sounding unit. That's one group of four. We're going to look at all six of these layers simultaneously, which I'm calling here SSU plus MSU. We're going to look only at the microwave sounder unit measurements there in the lower stratosphere and in the troposphere. They'll be shown in green, MSU. And we're going to look only in the troposphere, at the lower troposphere and at the total troposphere. So those are the four groupings. And again, the four geographical domains we're going to be looking at. Additionally, in the thought experiment, we look at 8 different assumed monitoring start dates. The first one is in 1860, which is near the beginning of the CMIP-6 simulations of historical climate change. Then we'll look in 1900, each time marching forward 40 years in time. We'll look from 1920 to 1959, which is a period without major volcanic eruptions, 1940 to 1979, 50 to 89, 60 to 99. This period is one of high volcanic activity. It includes the effects of Mount Agung in the early 60s, El Chichon in 1982, and Pinatubo in 1991. A 1970 start date, and the final start date is the actual satellite era, the 39 years from 1986 through to the end of 2024. And I'm going to include that because I'll actually be able to show you for that period a comparison between the fingerprint detection times inferred in these 32 individual realizations of historical climate change and the fingerprint detection times in the real world in the satellite data. Another reason for looking at those 8 different start dates is shown by this. So this shows you from a nice paper by Kachamathis et al. In geophysical model development, the solar forcing that was used in CMIP-6 and in CMIP-5, that's here in orange, and CMIP-6 in black, in terms of the total solar irradiance here in watts per square meters. And you can see, if you look at the black curve here, that there's some interesting changes in solar irradiance over time. So these peak-to-peak differences here, this is the 11-year solar cycle between solar maximum with maximum solar irradiance and solar minimum. But you can see that the 11-year envelope also changes as a function of time. There are interesting low-frequency changes in the amplitude of this 11-year solar cycle. So these different monitoring start dates will pick up some of this rich variability, not only in the volcanic aerosol forcing that I just showed you, but also in the solar forcing. And we'll be able to see how detection time is influenced by things like these changes in volcanic activity and changes in solar radiance. And just going back to this figure here, one of the things that you can see in these upper layers here is you can see this 11-year solar cycle very nicely in the thin upper atmosphere here. You can nicely see in both the simulations and in the observations. So in the purple line and, and in the black line, this 11-year solar cycle here, it's much more difficult to see that in the noisier troposphere. All right, so now I think I've outlined the components of this thought experiment, and let's look at the first 40 years. So again, our earliest start date is 1860, and the actual CO2 change that was used in the CMIP-6 simulations of historical climate change is small. So from 1860 through to 1900, 40 years later, you only have roughly a 10 parts per million increase in CO2. That's our best understanding from the ice core data of how CO2 actually changed. If you look in the model simulations from CMIP-6, from 1860 through to 1900, again, this is the multi-model average in black. The gray are the individual model realizations. It's noisy. There's very little change, overall change. The trend in tropospheric temperature over this time period is very close to zero. You can see in the troposphere the very large cooling of the troposphere caused by the eruption of Krakatoa in 1883. And these other vertical lines, these are the times of solar maximum. And again, it's more difficult to see in the troposphere that solar-induced warming of the troposphere because the troposphere is inherently much noisier than the mid to upper stratosphere. The bottom line here is that it seems like it's very unlikely that there would have been an identifiable human-caused tropospheric warming signal in these first 40 years here, from 1860 through to 1900. But in the stratosphere, if we look at the temperature of the upper stratosphere in the model simulations, you can again now, as I just explained, nicely see this 11-year solar cycle. You can also see the very large warming of the stratosphere caused by Krakatoa. But the key thing here is that there's, even with this modest 10 parts per million increase in CO2, we're already setting up a stratospheric cooling signal. And what I'll try and convince you is that after about 1885, we can discriminate this human-caused stratospheric cooling signal from the rather small background noise of natural climate variability. So a fundamentally different signal-to-noise situation in the stratosphere relative to the troposphere. So here you can see now, first of all, for the three SSU channels, 40 to 50 kilometers, 35 to 40 kilometers, and 25 to 30 kilometers. The black line, again, is the multi-model average. The gray lines are the 32 individual realizations here. The blue line here is the average of the satellite temperature data from 1986 through to 2024. And the red is the trend in the actual satellite data. The green lines, again, are major volcanic eruptions. Here's Krakatoa, Santa Maria, Nova Erupta, Mount Agung, Fuego, the El Chichon eruption in 1982, Pinatubo, and here is the recent and highly unusual eruption of Hunga-Tonga in the Pacific that injected massive amounts of water vapor into the stratosphere and even into the mesosphere above the stratosphere. I'm fascinated by this simple picture, simple but contains a lot of information. Again, you see these ripples here, these 11-year ripples. This is the 11-year solar cycle here. You can see that over time, there's been this progressive cooling of the stratosphere. And you can see that that cooling really began to accelerate after about 1960 as we ramp up CO2 and also as we increase the depletion of stratospheric ozone caused by chlorofluorocarbons here. So there's this very large increase in the rate of stratospheric cooling. You can also see other features that I mentioned earlier. So the signatures of volcanic eruptions are clearer in lower down in the stratosphere where most of the aerosol resides. These are the data sets we're going to use to try and do fingerprint detection starting back from 1860. And again, what I'm going to try and convince you is that in the stratosphere, after about 1885, so only 25 years after beginning to monitor temperature in 1860, I'm going to try and convince you we could have identified a human effect on stratospheric temperature. These are what these stratospheric fingerprints look like, and tropospheric fingerprints. This is in this 6-layer space. So the 3 MSU layers and the 3 SSU layers. And what I've done is I've calculated the fingerprint of response to human effects on climate for 3 different periods, 1860 to 1882. So this stops this period before the 1883 eruption of Krakatoa in order to avoid volcanic contamination of the fingerprint. This is a later fingerprint with larger CO2 changes, estimated over 1920 to 1959. The fingerprint, I should point out, is the leading empirical orthogonal function of the multimodal average changes in the vertical structure of atmospheric temperature. And this is the fingerprint over the most recent period here. It starts in 1994 in order to avoid the effects of the 1991 Pinatubo eruption on atmospheric temperature. And what you can see here in these fingerprints, the interesting thing, I think, is that even back here in this early period, with a modest increase, human-caused increase in atmospheric CO2, we're beginning to set up this Manabe predicted pattern of tropospheric warming and stratospheric cooling. It's noisy, and later, with larger CO2 changes, we begin to see it more clearly. And we begin to see this Manabe and Weatherall predicted amplification of cooling the higher up you get in the stratosphere. And in the most recent period, this distinction between tropospheric warming and stratospheric cooling becomes clearer still. The same is true if we look in the troposphere. So now I'm only going to look at the 2 tropospheric layers, the lower troposphere and the mid to upper troposphere. In the early period, with modest CO2 increase, what you pick up really doesn't look like an anthropogenic fingerprint. It looks like El Nino. It looks like the signature of ENSO. So the largest loadings here are in the tropical atmosphere, and you see amplification of warming in the mid to upper troposphere consistent with a moist adiabatic lapse rate. As you move later in time and the CO2 forcing becomes larger, look at this fingerprint here. This looks much more like what we actually see in the satellite data, with Arctic amplification associated with the profound retreat of Arctic sea ice over the last 40 years or so. So what I'm arguing here is that in the troposphere, it takes longer until this anthropogenic fingerprint sets up. Well, let's go back to a slide I showed you a little earlier, where I showed you this measure of pattern similarity between the search for human influence fingerprint and the actual satellite data. And I described features like the impact of Pinatubo, so why this pattern similarity goes negative around the time of the Pinatubo eruption, and I described the overall trend. But now what we're going to do in calculating detection time is we're going to look not just over the full 39-year period. We're going to look over the first 5 years, the first 6 years, 7 years. So we're going to march forward in time. And for each of these trends of 5 years, 6 years, 7 years, we're going to look at the noise on the same time scale, using the control run data projected onto the fingerprint. And that enables us to look at this signal as a function of time scale. So this is, again, for an assumed 1860 start date, and we're marching forward in time. And the first time period here is 5 years long, 1860 through to 1864. And the longest time period is 40 years, going through to 1899. And what you can see here is this really fascinating behavior. So look, for example, at, and these signals are for these 4 vertical domains. The 3 stratospheric layers, all 6 layers, the 3 lowermost layers, the lower stratosphere and the 2 tropospheric layers, and the 2 tropospheric layers only. And I'm looking at the signal behavior as a function of timescale L, with L increasing by 1 year at a time from 5 years through to 40 years. So in all four of these vertical domains, what's happening here is that after Krakatoa, the signal is going negative because the troposphere is cooling, the stratosphere is warming, and that's the converse to the searched for human influence fingerprint. You can also see here these interesting little dips. This dip here is around 1871. That's as we're transitioning to solar maximum in 1871. And in solar maximum, the sun is heating the stratosphere and it's heating the troposphere, which is the converse of, in the stratosphere, the human influence fingerprint. So you can see the signatures of natural forcing in this evolving signal as a function of time. Like I said, we do the same thing for the control run, projected onto the same human influence fingerprint. We can look at the noise as a function of time scale, and that enables us to look at signal to noise as a function of time scale here. And what you can see here is that in the stratosphere, the purple layers here, there are 32 lines here, one for each realization. By 1899, we can, with high confidence, pick out a human-caused stratospheric cooling signal relative to intrinsic variability. We can do the same thing for all 6 layers here, the stratosphere and the troposphere. But in the troposphere only, and in the 3 lowermost layers, the signal has not, repeat, has not emerged from the noise of natural variability by the end of record in 1899. If you look at later start dates, this is summarizing, first of all, before looking at later start dates, the fingerprint detection times for an 1860 start date for these 4 different vertical domains. And if there's a big magenta dot here, this is the stratosphere only, the SSU only. It means that we can detect in at least 2/3 of the 32 individual historical realizations. And the key point here is that for all 4 of these geographical domains, the globe, the northern hemisphere, the southern hemisphere, and even for this very small area from 40 to 55 north, we can identify a human fingerprint in mid to upper stratospheric temperature. And for all 6 layers in 3 of these 4 geographical domains, the exception being the smallest domain here, again, we can reliably identify a human fingerprint on these 6 layers. Now, if you look at the green and the red here, so the 3 lowest layers and the tropospheric layers only, there's very little detectability, which is what you can see here. Most of these orange lines and green lines don't cross this black line here, which is the 1% significance threshold. So in order to detect a human fingerprint, we have to rise above this 1% significance threshold and then remain above it for all values of L that are larger than the time when you first poke over this black threshold here. So again, take-home message: for an 1860 start date, we can detect with high confidence in the mid to upper stratosphere, with high confidence, but a little later in all 6 layers, because the 6 layers, the dark blue, include the noisier troposphere, which the magenta do not. Very little detection in the lowermost layers. If you look at a later start time with larger CO2 forcing, you can see that it's not taking as long now. We get earlier detection. Look at this, compare this. It's taking about 25 to 30 years in the magenta and the blue. It's not taking as long with the larger CO2 forcing if we start monitoring in 1920, and we're beginning to get more detection, more green dots and more red dots in the lower atmosphere. This is what happens for the most recent start date, 1986. We can detect with high confidence very quickly in every domain and in every vertical grouping of layers that we look at. And if you're wondering about these open symbols, these are the actual satellite data. So what this shows is that in many cases, but not all cases, the detection times that we infer in the actual satellite data are in accord with what we get when we look in model world only in these 32 individual realizations of historical climate change. So the bottom line of this new work is this: as Fengfei mentioned, a human-caused stratospheric cooling signal would have been identifiable by approximately 1885, before the advent of gas-powered cars. Our results suggest that a discernible human influence on atmospheric temperature has likely existed for over 130 years, which quite frankly surprised me. The notion that we could, back in 1885, if we had been able to measure stratospheric temperature, have said with high confidence, this is not natural, I find that surprising. Just finally, what about the future? Well, I haven't shown you the projections of future climate change in the stratosphere or in the troposphere, and I'll do that now. So we focused on 1860 through to 2024. These are the projections from the same models, the same 9 models, 32 realizations, out to 2050. And I think the remarkable thing is that the projected changes over the next 26 years, so out to 2050, are larger than the changes we've actually observed over the last 39 years, which is sobering. Stratospheric cooling, if we're even in the ballpark with our understanding, is likely to be large over the next 25 years. The same is true for the troposphere, for the lower troposphere and the mid to upper troposphere. The projected changes are of order up to several degrees over the next 26 years. We ignore these changes at our peril. Just finally, the atmosphere is a fragile shell, and what this research shows is that we profoundly influence the temperature of that fragile shell. I love this. I love this picture. This isn't AI. This is a Japanese artist who figured out clever ways of launching flowers and bonsai trees into the stratosphere and photographing them. And to me, it's a metaphor for the fragility of life in this thin shell that we inhabit. It really is incumbent on us to understand how and why this thin shell is changing and how long it has been changing. Thank you very much for inviting me to talk to you today. Again, my apologies for last week and for messing the timing up. I'd be happy to answer any questions you might have about this work.
Okay, thank you. Thank you, Ben, for taking this very nice seminar. So if you have any question, you can just unmute yourself and ask Ben, or if you if you are not available for them, you can also write your question in the chat box. I will read it for Ben. Jian, yeah, take away.
Hello, Ben. Yeah, fascinating story. I really enjoyed it. Just a quick question about this, the curve of signal noise ratio curve. I'm just wondering to what extent the cooling in the stratosphere may be attributed to ozone forcing, ozone depletion, maybe prior to year 2000.
Yeah, great question. And what's really necessary is single forcing simulations with high vertical resolution models like Wacom and other models that nicely separate the individual influences on stratospheric temperature of human-caused ozone depletion and human-caused CO2 increases, and increases in other gases too, like chlorofluorocarbons. It would be wonderful to have ensembles of those single forcing simulations in order to answer your question quantitatively. Susan Solomon knows and Chung know more about this kind of stuff than arguably anyone else in the planet. And they are concerned very much with the same question. How can we get a better quantitative handle on the relative contributions of these two things, ozone depletion and CO2 increase, as a function of altitude?
Yeah.
We probably don't have such a good quantitative understanding of that vertical breakdown at the moment. So I'm hoping that perhaps in CMIP 7, the next phase that's currently underway, we will have a better breakdown through single forcing simulations with high top, high vertical resolution models of the relative contributions of ozone depletion and CO2 increase.
Yeah, so I just left PNNL a few months ago, just escaped from version 2 in time. And I know actually those ensemble simulations, individual forcing ensembles are already available with both ANCAR CSM model and DOE model as well, EtherSM. So there might be single forcing, yeah, ozone, CO2, aerosol, land use, yeah, already existed.
And do you know the ensemble size for those?
At least 20, to my knowledge. Yeah.
Wow.
Yeah, I think just good enough probably for this purpose. Yeah.
That would be terrific, particularly if they've saved not at the standard pressure levels, but at at enough vertical pressure levels to enable us to calculate synthetic SSU temperatures. So that was one of the difficulties that I didn't mention with CMIP6. We required this so-called PLEV 32 data. So not the standard pressure level data that most modeling groups supplied, but the high vertical resolution stuff.
So it's done in Ruby's group. So if you're interested, you might want to contact Ruby for that. Yeah. The DOE combo. Yeah.
So this is both E3SM and WACM, or
it's CSM to my knowledge. It's just CSM individual, yeah, forcing ensemble. May not be not WACM. Yeah. Maybe it's no enough vertical resolution for the stratosphere.
Do you know whether these models have prognostic ozone? So is this specified ozone or is this prognostic ozone?
I think it should be prescribed ozone. Yeah, not prognostic. No.
I see. Okay. Terrific. Yeah, I will. Thank you very much for that suggestion. I would love to look at them. Like I said, I'm failing retirement pretty miserably at the moment.
All right. Yeah. Thanks for talk. Yeah.
Thank you.
Yeah, thank you. So welcome to China when you have time. Maybe we can have a seminar in person.
Well, yes, that would be terrific.
Yeah. So yeah, I have also a question. So I'm just wondering why is the stratosphere rather than the troposphere to detect the signal first before, yeah.
Well, that's a great question. And let me see whether I can answer your question by showing, yeah. Yeah, this, can you see this or?
I didn't see it. Could you share it again?
Yeah, I'll try sharing it again. Yeah. So one of the reasons is this. Well, sorry. If you look in the stratosphere, just compare above 30 kilometers here. Compare the fingerprint, and these are actually the leading noise modes in the control runs from these 9 different models. What you can see is they're almost orthogonal. So the human fingerprint is this latitudinally coherent cooling, with cooling amplifying the higher up you get, whereas natural climate variability doesn't look anything like that at all. But in the troposphere, there's greater similarity between the search for human influence fingerprint and natural variability, because ENSO has such a big signature in the troposphere. So what I'm trying to say is, in the troposphere, there's greater pattern similarity between the search for human influence fingerprint and natural climate variability than there is in the stratosphere. Also, the noise levels are larger in the troposphere than they are in the stratosphere. Most of the weather is in the troposphere. The stratosphere has less intrinsic variability and a very large signal. You know, the signal that Manabe predicted all those years ago is of order 2, 3, 4 degrees Celsius cooling of the stratosphere over the satellite era. That's huge relative to the intrinsic variability. So the stratosphere is a good place for pattern reasons because the human influence fingerprint doesn't look like the patterns of intrinsic variability. It's a high signal region where the predicted signal of combined CO2 increase and ozone depletion is very large. And it's a lower noise region, the stratosphere, than the troposphere.
I see. So it seems, yeah, so it seems the signal to noisy ratio it determines the stratosphere is more detectable, right?
Yep. And again, let me emphasize that that signal to noise ratio is not just something that I'm looking at in global mean terms. So the signal to noise ratio, as recommended by Hasselmann all those years ago, incorporates this pattern information that you see here. And that's really critical because in the stratosphere, again, above 30 kilometers, the human influence fingerprint just doesn't look like any kind of patterns of intrinsic variability. And it doesn't look like patterns of solar forcing and volcanic forcing, at least not on 40-year timescales. So I didn't mention this, but in an earlier paper, we did the signal to noise analysis, not relative to control run estimates of intrinsic variability, but relative to the so-called CMIP5 historical NAT simulations. So these were simulations with historical estimates of changes in volcanic and solar forcing and intrinsic variability in there. And you could use those as we've used control runs here to ask, could some combination of changes in the sun, volcanoes, and internal variability give you this kind of fingerprint pattern? And the answer was no.
I see. Okay, great. Thank you. So, anyone have a question?
Hey, Ben, I have a question.
Yes.
Can you hear me?
Yes, I can.
It's a technical question. I noticed that your research is more about the change pattern of the air temperature. It's a 2D dimension time evolution in satellite data or model simulations. Nowadays, with the popularity of the fingerprint, it is more used in many other studies, such as precipitation and tropical circulation. So they often focus on a regional signal while calculating the area mean. Then the signal turns into a 1D dimension time evolution, and then they give each forcing or scaling factor to represent their contribution to the signal. I wonder how this is achieved.
Yeah, we use pattern information here, as I've tried to explain, but you're absolutely right. Other studies have done this kind of work just using spatially averaged temperatures. For example, I believe there's a paper by Duan et al. In 2019 that looked at changes in the amplitude of the annual cycle of surface temperature in nine different regions over the Tibetan Plateau, mid-latitudes of the Northern Hemisphere, high latitudes in different domains. And I think they do exactly what you described. They use a sort of classical regression-based approach operating on time series of spatial averages in these different domains, which is fair enough if you think that you don't really have detailed spatial information in those domains. That's the best you can do, a spatial average. But here, at least in model world and in the satellite data too, we do have spatial information. So you can play these games where you look at a global geographical domain, Northern Hemisphere only, Southern Hemisphere only, and like I said, even a very restricted latitude band between 40 and 55 degrees north, to see how signal detection depends on the size of the domain that you consider. I don't know that I've answered your question, but that's one of the things I was trying to get at here. How does indeed detection time vary as a function of the geographical domain you're considering? And one of the lessons learned, surprisingly, was that even for this very restricted latitudinal domain between 40 north and 55 north, if you could measure in the stratosphere, the signal was still big enough to be discriminated, even in that first period with a monitoring start date in 1860. Does that sort of answer your question?
Yes, maybe I see many papers, and in their methods, they refer this or regression method. It's like a regression method, I think.
That's right. Some of the first folks who worked on this, Miles Allen and Simon Tett and others, cast this as a regression problem. And there are different ways, many different ways of doing fingerprinting. Some fingerprint methods lump everything into a single spatiotemporal vector. So they incorporate both the time information and the spatial information in a vector, in the observations and in the simulations, and then calculate this scaling factor to look at the strength of the model predicted spatiotemporal vector, say, of surface temperature change in the observations. I'm not doing that. I'm looking at signal to noise as a function of time scale, which I think enables you to, at least in my opinion, more easily understand if you get a positive result, if you get fingerprint detection, where is it coming from? Is it coming from spatial similarity? Is it coming from unique time evolution behavior that's common to the simulations and the observations? Doing it in this perhaps more simple-minded way that I do enables you to better see the stuff that I mentioned, the impact of solar variability on detection time, the impact of big volcanic eruptions on detection time. That's a little more difficult to do when one is casting this as a problem that just operates on spatiotemporal vectors.
Okay. Okay, I see. Thanks for your answer.
Yeah. Ili is my student, so she currently doing some work on the upward shift of the westerly jet. She detected that this signal has already emerged in observation. Yeah, so she also uses the detection and the attribution. I think it's quite partly tied to the tropospheric temperature change. So yeah, maybe I can discuss it with you in emails with more details.
Yeah, that's very interesting. I mean, is that a consequence of the lifting of the tropopause?
Yeah, I think so. Yeah,
Yeah.
we use the lifting of the troposphere to developed by O'Gorman to address the issue, and found it explained very well. So yeah.
Nice. Yeah, I would be very interested in that. We published a paper in Science back in
I know
2003 where we used tropopause height, the pressure of the lapse rate tropopause, as a detection variable, and it was interesting to be able to show that this lifting of the troposphere is in accord with basic physical expectations and is there in models and in observations. And I'm super happy that you're looking at that, because I haven't seen a lot of work that has updated that early analysis. That was 2003 with very early CMIP3 simulations and very early reanalyses from NCEP and from the European Center. So one could and should do a much better job with those fingerprint studies with tropopause height now, with better simulations and better reanalyses.
Yeah, you're right. Yeah, so that's what we're trying to address. We found this in several IPCC reports. They say they uplift our troposphere in the IPCC report in the future warming scenario, but whether it has emerged in the observation, I didn't find any related study according to our knowledge. So we trying to do this, and what we found this signal is quite robust across different observations. So yeah, so. Yeah, I can send you via email about details. Yeah.
And it makes sense then that it would have implications for the height of jets.
Yeah. Okay. So yeah. So okay. So if we didn't have more questions, maybe we can just stop here. So we almost 1 hour and 20 minutes. So thank you again, Ben, for attending this seminar, and thank you for telling us this very interesting story. We hope to see it in a journal. Yeah.
Yeah. To that point, you're some of the first to see this. So this work is currently in review at PNAS, and I hope to have a decision relatively soon, and hope that this will be published in the next several months or so. I'll let you know about it. But it does seem, in terms of communicating, that this is a long-standing problem. It seems like this is the kind of thing that could and should be done with other variables too. I mean, there's nothing special about atmospheric temperature. One could do this with a variety of different other variables too, to get at the question, when could we have known?
You're right. Is passion is, I think it's quite develop a new method to answer what happened if we didn't have the observation, how to address this issue. So it's quite a new method, I think. Yeah.
Well, it was inspired by Einstein. He was very fond of what he called Gedankenexperimente, which literally translated means thought experiments. So things that he could do in his head, involving trains moving, elevators falling and stuff like that. And I love that concept of doing a thought experiment and with model simulations. That's the beauty of these simulations, is that they start in 1850, and yet most of my attention and most of the attention of my colleagues has been on the observational period, comparing simulations and observations. But there's a wealth of information, I would argue, that's about basic signal-to-noise properties of the climate system that's contained at the beginning of these simulations.
Yeah, great. So look forward to seeing it in PNS. Yeah. So maybe next time you can come to China to take a in-person seminar. So welcome.
Thank you. And thank you again for giving me this opportunity.
Okay. See you. Bye.
All right. Goodbye, everyone.
Bye.